Okay, solution. Please see the link. You do? That's the link is expired because I realized not this class but another class I was solving it. And one of the students just cut paste from whatever I solved and just submitted it. He was very smart. But anyway. So let's do a FED for this. Right? So if you want to do a FED, what do? You walk over the border, include the surface force, then you include the body force, and you're done. So let's take a start point here, for example here, and then I walk clockwise. Right? So the first thing I caught is the interaction between the surface of the water and the wall. You see the wall and the surface. So this is the wall at this point. You see that point is right here. So the other side is this wall, and the other side is the fluid, the water. So the question is, what kind of force do I get? You get some sort of normal force and some sort of friction, right? So what's the direction of friction? If you go this way, the direction of friction is this way, right? So you get components like that. And then let's continue walking. Your next point, you get another force, another friction. Continue walking, you get that. So in fact, if you really want to include that on your FED, which you should, you're going to have lots of infinite number of forces. So in fact, in real life, you have a distributed load like this, and also for the viscosity. And you cannot quantify that unless you solve it, because it's unknown. So you have something like that is unknown, and then at this point, what do I have? The water is leaving the domain. I have an inertial. You guys have dynamics, right? So in your FED, you put inertial load. What is that? Rho A V squared. Now you can either do that or get it from the momentum equation. Right? So rho V squared at point A. This comes from all this integration of that. At point B, this point B. This B is this A. So rho A B, VB squared. And it's going that way. Now, later on, I'll show you why that we get the force there. It's an inertial. This is not the actual touching steering. Touching load is a inertial force. Just like you did in dynamics. You add inertial loads to your FEDs. And you use dash like this. Right? Dash vector here to show the inertia. The real force is solid. The inertial load is dashed. Now, continue working. What do you get here?
Same thing.
Same thing but the other side. Again, you have pretty much like same, but the other side. Continue working. You see, this is not my system. This nozzle is not my system is the water, the control volume, right? So if you continue, I can't just put F over 2 on this. So that's the way I grade it. If you put F over 2 on your control volume, this quiz, you don't get good grade for this quiz, right? Now what do I have here? I have a pressure load, which is a uniform pressure load. You can replace your point load, or you just show the uniform. This is a uniform. What's the value? Do I have the value? Yeah. The value of this is 200 kPa. What else do I have here? Again, inertial load. And what's the inertial load? Rho, but it goes this way. Rho A at A times V at A squared. But it goes negative. What else do we have there? Did you add inertial load in your dynamics to your FED? Really? That means when you did FED in dynamics, you didn't add inertial load to the FED?
I don't remember it. We may have, but I don't.
Yeah, the problem is, here's the thing. I do have some student coming to me and I say, well, it's been a long time and we don't remember anything at all. And in that case, yes, but if you are 100% sure you did not add initial load to the FED, there's something really wrong, because in the dynamics there is a course called machine dynamics or dynamics of machine. You really need to do every single FED. You're going to have like 20 FEDs. Every single FED is like a gear that is rotating and moving, and you have to add all those initial loads, otherwise your solution is totally wrong. Make sure, so review dynamics, review everything. So these are the initial load. This one, again, dash is not the real load, it's a dash, dash, dash. But this one is solid, the pressure load is solid as a real load. This one is inertial load. Now, continue working and you come back, start going. Done. Do I have the gravity now? These are the surface force. I'm done with the surface force. Do I have gravity? Do I have gravity?
Yes.
Yeah. Well, it depends which way the nozzle is pointing. We don't know.
Exactly. That's the answer. Look at it. The nozzle is flat, like this, right? And this is the way I draw it, just to show is a cross section. We're looking from the top. So if I look from the top, the gravity is going down in the plane, right? It's not even in the y direction. Do you see that? So unfortunately, this problem they require a lot of three-dimensional visualization. So if you're not sure, make sure you go back. That's the reason I draw the 3D nozzle. It's not drawn in your book. I had to draw it to show you why you don't add gravity here. Why? Because gravity is downward. Yes?
How do we know it's from the top and not from the side, other than you just saying it?
Well, even if you look it from the side, right, the gravity is going this way, and you see my y direction is this way. You see that? That means if I look it from the side, like this, your gravity is going this way.
Mm-hmm.
So it's never in the y direction. Alright? So that's it. That's all I have. Now, you see the F/2, the force that I have here, it doesn't show up on this FED. And the students get really confused. So how can I find F/2? There is no F/2 in FED. Look, if I want to draw FED for the other one, the nozzle, not the water. Now you take your control volume around the nozzle. What do I get? You get F/2 here. F/2 here. Right? What else do we get? Opposite of this load here. You see that? And opposite of this load, the other side. You don't get anything from pressure, the inertial load. These are imposed on the water, not the nozzle. The only way nozzle is interacting is through, and also there is another load here. You see, this part, there is a load here. I just draw it like that. So the only way the nozzle gets the forces is through the interacting through this space with the fluid. You see that? The nozzle does not feel the pressure here or the pressure here, the inertial load. It only sees the surface loads on the fluid. So if you get the result of this, the result of this should balance with F/2. That means before, you see, these are the things is not shown in the book. And if you really don't go deep like this, you'll be memorizing. So when you go to the next course, I can't solve it. But you can, if you really go deep, you can solve every single problem. So that's the reason I draw this. Now, the conclusion of all this drawing is that, do you agree that the sum of these forces, if I can just say, if I find this and call it F surface, right? Do you agree the sum of F surface should be equal to F/2 plus F/2 on this system? Right sum force in y direction is 0 in this system. Right? Take your y positive here. what do we get? Negative f over 2, right? Negative f over 2 plus the integral of this f surface must be 0. Because what? Because the nozzle is not accelerating. The nozzle is in place. So what is that? F, negative f is equal to, positive f is equal to integral f surface. That means the sum of these forces is equal to value of f. Now what can I say? I can say that from this system, now I can go to this system. And I can say this very confusing distributed load that you cannot find it unless you use computer techniques. I can say, well, the only thing matters in the y direction is the sum of this distributed load, right? And I know the sum of it is equal to f, right? Or f over 2 one side, f over 2 on the other side. So I can do this. I can get rid of that and put the sum of it. Because if I write y momentum equation, the sum only matters, not each one of those at each point. So I can put f over 2 here and f over 2 here. Why? Because I already know from the nozzle system that the sum of them are equal to f over 2 for the nozzle to be in equilibrium. So you can do that. That's the thing that your book shows you. But there is a lot of reasoning why you just put f over 2 on the nozzle, you put it on your control volume, which is water. The y is what I explained. Now, you have your system, FED, now equation. Now, the question in the water is, the question in the book is find, let's see what the question is saying. It says, find the required force to keep this in place. How much force do I need to keep this in place? That means solve for F, okay? So what equation do I have? Let's write the equation. So I'm working here. One equation is continuity, which basically you will solve with that integral, but in this case you get what? Sum of rho A B must be 0, and this B dot N. B dot N dot A must be 0. So this continuity equation, momentum, let's write Bernoulli. Bernoulli says this is 2 point A and B. You have PA plus 1/2 rho BA square plus rho G BA is equal to PB plus 1/2 rho BB square plus rho G ZB. Right? And then momentum, you get this integral volume rho V dV plus surface integral rho V B dot N ds is equal to sum of it, extent of it. So let's work on these equations. First of all, can I write Bernoulli equation for a point? You see, I have a streamline here. Let's say you are sitting on the streamline here and you transverse all the way to B, right? Can I write Bernoulli equation? Is that a valid equation? Why not valid?
No difference in equation. The Z, ZA and ZB.
No, I'm saying that is this. You see, what was the assumption to write Bernoulli equation? Frictionless. Can I make an assumption? Is this frictionless? Consider the core, the streamline that goes through the core of the pipe. Forget about this surface here. Just consider the core. Can I write that equation for a streamline that passes through the core? Yeah, I can. In fact, you can immediately say that this equation in general is not valid. Why? Because a friction, you see? Where is the friction? This distributed load. You see that? So it's gonna add effective friction and that effective F, and these are all correlated. So there's gonna be some pressure drop, like you saw it in the lab 2 weeks ago. But for a moment, let's say it's frictionless. So I just take one stream in the core, and I approximate it by the way. So I have, this is valid, right? What about continuity? Is that valid equation?
Yes.
What was the original continuity equation? Let me write the original continuity equation. This is the original continuity equation. The general, I shouldn't say original, the general continuity equation. So what happened? What did I do with this term? The time derivative with respect to t? Do I have? We assume that it's a steady state. That means in time is not varying. You see that the streamline are not fluctuating. Now, if you really in the real life, if you have a case that you get bubbles and you get all variation in the vorticity field and the streamline, not even this equation is valid. So in this equation always valid, no matter what you get. This is just a crazy thing. This is the most general, always valid. But look, I assume this is zero, the steady state. So I get that, and I expand it with sum over first faces, rho I, v dot n, ai zero. That's exactly this term. Because you see, in the next midterm, I'm going to ask you to do these things. You can't just memorize this equation in the appendix. You really need to understand how this equation is obtained from the general form. All right? Now, in this case, can I even simplify this a little bit further?
Take out rho,
Take out rho. Why?
because it's water on both ends, so
It's
rho's.
incompressible.
Yeah.
If this was like a very, you see, water is a dense fluid. Assumption of incompressible 99.9% is valid. It's extremely hard to compress the water. It is possible, but it's not usually the case. So in this case, the water is incompressible. You can just take this rho out and just same rho. So look, rho times the sum is equal to 0. What can I say? The sum is equal to 0, right? So you don't even need to write rho here. So that's the first equation. Second equation, Bernoulli already mentioned, we assume it's frictionless. So this also valid. These two equations are valid. What about the third equation? Momentum. Let's expand it. So the first term, should I worry about this first term? The time derivative of whatever you have is 0 as long as it's a steady state. So this is what? 0. Now let's expand this. What do I get from that if I expand? I get integral over phase 1 rho v dot n ds plus integral over phase 2. Let's call this phase 2, phase 1 rho v dot n ds plus integral over phase 3 rho v dot n ds is equal to sum of f external. So which one is phase 1, phase 2, phase 3? Let's call this phase 1, right? A. Let's say A is phase 1. Let's say B is phase 1. This phase 1, right? Phase 1. Let's say this is phase 2. And then the one around it, this is phase 3, is a cone. Right, you see that? Is a cone. So we have 3 phases. So I expand the ring, and no longer have the ring because I expand into 3 separate phase integral, surface integral. Now, for phase 1, because this point B, I just put B. Phase 2 is right here. I just point A, and this is just the surface or the cone. Let's put the cone here. Now let's expand this integral. What do I get for phase one? If I take the integral of phase one. Look, I assume the velocity here is constant. Do you see that? Constant velocity. So you have a uniform velocity here. So if I take surface integral over the face B on the top, what do I get? I get rho. What's the velocity there? Say VB, right? Is it positive or negative? See, this is my positive y. It would be positive, going this way, right? Rho VB, and then what do I get for V dot N at that face? Yeah. You see, N is what way? This is N. You see that? This is N. This is N. N is always, one thing I do in the next meeting, I will just give you something and say draw N, normal vector. N is always outgoing. That means N is this way here. You see that? N is this way here. So V dot N, as explained, V is this way, N is this way, V dot N is what? Positive. So it's just positive. This term is positive. VB. Fine? When you take the integral and finish, it's just integral over that face. So what do I get? Integral over ds over v? What's the integral of ds over v? Yeah, the surface of v. Right? So you get vb, rho vb times the parenthesis is positive vb times the area at point B. You agree? You go to the next one. Now do for A. Where is the A? A is right here. So what's the velocity at A? Is it positive or negative?
It's positive.
It's positive, going up. So you get rho A, VA positive. And what about V dot N? Is it positive or negative?
Negative.
It's negative. N is this way, V is this way. Two vectors, they have pi degrees or 180 degrees opposite phase. You see that? You dot product, you get negative VA. Negative VA. And then the area at A, or S at A. You can get, say, S at A, because after that, when we do surface integral, you say surface area at A. All right? What else? What do I get for that? What do I get for that? Whichever?
Zero.
Okay, yeah. Whichever. How many? Whichever you got?
That, I think it's my fourth, but I was gonna talk to you after, cause some of them aren't loaded, so I need to make sure that I got them.
Okay, okay. All right. This is zero. If you don't know why this is zero, you need to come to my office. Because I have said it like at least 6 times so far. I can't really say it one more time. So this is zero. And then what do I get for right hand side? The external loads. What do I have external load? I have one load here. You see that? The pressure load. What's that? The pressure at A. This should be equal to pressure at, did I call this point A? Yes. Pressure at A times the area at A, positive or negative? You see, look at it. The pressure at
Positive.
A, positive or negative?
Positive.
Positive. Do I have external pressure at point B on the top? Do I have PB?
No.
Is it, gauge pressure is zero, there is nothing this way. Plus, what am I missing? Can you tell me? Look at it, what's the external load? I already include the force, the pressure force, no pressure force here. And what about the surface force we have, which I had? F over 2, F over 2. So you're gonna get negative F over 2, negative F over 2. These are some of our external loads. Now guys, look at it. These two, you see that? These two are what? These two are forces. Do you see that? Let me write it here. These two, if you bring everything to one side, what do you get? You get rho VB squared times AB minus rho VA squared times A at A is equal to PA A at A minus F. If you bring this to the right, we're gonna get the same equation like vector static summation of force 0. So that means we can consider these two as the force on the FED, just like we did in the vector static. We draw the system and we include all forces. And we said some of the forces must be 0, right? So that means even though these are not the actual load, if you put it on the FED and do the summation, you will end up always with the equilibrium equation. Now you can do it either this way, or you can just say my real load is this F and P, and I'll just expand the momentum equation in order to get to that. But the way they do that, they also put the inertial, you see this is dash, 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 dash. The inertial load also on the FED. These are the dash loads, the inertial load. Inertial, just like dynamics. In dynamics, it was MA, acceleration in X, MA, acceleration in Y. You would put acceleration on your FED with dash, dash. If you haven't done that, big serious mistakes. You really need to go back and redo the entire dynamics. You have to put your acceleration on the FED. Alright? So these are the equations I have. Now let's solve it. Let's put the numbers here. So the first one, let's solve the rest of it there. The first equation, continuity. I write what? A1, expand this equation between A and B. So you get A at A times B at A at B times B at B. But A dot N is 0 here. You see that? E dot N. So from this equation, you can say B at A is equal to A at B over A at A times VB. And if you put pi dB over 2 square, pi dA over 2 square, VB, pi cancel out to cancel out, so you get dB over dA square VB is equal to dA. Now let's substitute numbers here. So dB is the diameter at point D, right here. The diameter is given in the book is 25 millimeter, and the diameter, we need dA, the diameter here is also, how much is it? 100 millimeter. So substitute there. So you get dA is equal to dB, diameter here, which is 25 over 100 square dB. So this divided by that is 4, 1/4 times the square, 16. That means VB is 16 times VA. Right? So that this is just continuity equation. We have already solved it. Right? Then the next thing, Bernoulli equation. You see, when I write the equation, put a check mark. Do not solve the equation. Even if I could solve it here, I see some students, they write the equation, when they go plug the number, the diameter. Don't do that. You have to first write all the equations just like I did. You see equation 1, equation 2, and equation 3. And after you populate all the equations, then you go solve it. That's just like vector statics. Nothing is different. It's just if you have done vector statics very well, you should be able to do all courses exactly the same. Now, this is continuity equation. This is continuity equation now. Bernoulli equation. Let's write between A and. Do I know the pressure at A? You see PA, I'm doing this. Do I know the pressure at A? Yes or no?
Yes.
Yes. 200 times 10 to 3. Pressure at A plus 1/2 of rho 1000 times VA. Do I have velocity at A? No. VA squared plus rho G ZA. Look at these two terms, rho G ZA, rho G ZB. Is there a ZB ZA different
No.
between? No. Why? Because it's just flat. Again, if you don't understand that, you need to come to my office, please. It's too late. So these two terms doesn't exist. So you go to PB. What's your rise for PB? The pressure at B?
0.
0. Plus 1/2 of 1000 times VB squared. So instead of VB, you see, I substitute from here, this equation. You see that? So 16 VA, or simply this is VB squared. So 1/2 of 1000 times 16 VA squared is equal to 0. Yes.
Why can we use this equation now? What we said earlier is that Bernoulli's equation didn't work with the, no friction.
Well, as I mentioned, this equation is approximate. It's not exact. So we ignore the friction which comes through this surface of pipe and it distributes through the shear stress everywhere. We said this is frictionless flow when you write Bernoulli. In other words, if you just consider you're just inside this, you don't see the wall. Inside this, from A to B in the straight line. You almost frictionless, but the real thing is not frictionless. The real thing you have friction, you have pressure drop. Next chapter, when you do the energy equation, you subtract this by L plus minus HL, and you get more accurate result. You'll see that. But right now, let's say frictionless. All right. All right. So solve this for VA. So you get what? If you solve that for VA, you get 500 times 16 square minus 500 times VA square is equal to 200 times 3. And if you solve for VA, you get, with a calculator, divided by 500. One point. And you gotta do also square root. Square root. So you get VA is equal to 1.252 meter per second. Right. Now what can I say about VB? Substitute here. VB is equal to 16 times VA, 1.252. That means it's equal to 20. .04 meter per second. VB. Alright, so double check that.
Yeah, that's what I got too.
You got the same value? Alright, so then, let's see if we, then the way we do that, we say we got VA, VB, almost 50 minutes. We solve the last equation. So this is the last equation. Substitute here. So rho 1000 times VB 20.04 square times AB I times 25 divided by 2 1083 square minus 1000 times VA 1.252 times minus 1000 this is square times AA, which is pi over 2 right here pi times 100 divided by 250 10 to negative 3 square, right? Is equal to PA. PA was 200 10 to 3 Pascal times AFA, which is pi 50 negative 3 square minus F. Solve this equation for F. One equation, one unknown. You get F is equal to, put it in calculator, you're almost out of time. 1000 times
This equation.
20.04
Yeah.
square times pi.
Honestly, if I had like candy strings, but like it's just on top of it.
I got it. She can just sit and stare at this shit for hours.
You have everything else in there.
I
Could you imagine?
got a 2.5-year-old.
So basically, have let me just plug everything in.
That's the area.
Yeah, let me just plug everything in, just try to.
1.386 kilonewton. And it's positive, should it be positive?
Yeah. Yes.
Why? Because look, it's the force that applies to the total volume from this nozzle, it should go down, otherwise the accelerator goes down. I mean, when I say up or down, I'm talking about in the air.
Yourself.